So, the last talk of today and the second lecture of the Professor Gavrilov is going to talk about introduction to the center focus problem for plane polynomial vector fields.
Thank you.
Okay.
So in this second lecture of the very short introduction to the center focus problem, I shall, in fact, finally say what is the center focus problem from my point of view. And after this, we shall explore some non-answered questions around the center focus problem. So we stopped yesterday on page 8. Page 9 was the Poincaré-Lyapunov theorem, which says that if the linear part of our system is non-degenerate, then the two definitions of center, the first one of Poincaré, which is geometric and is valid only for real differential systems, and the second one, which is more analytic, which says there is a first integral at the origin, which in fact can be extended in a complex domain, obviously, they coincide. So this is good for us. In fact, this will be our basic definition of center. Center is a singularity which is non-degenerate and has, therefore, according to one of the two definitions, Poincaré-Lyapunov theorem, a first integral which is analytic, and automatically we can suppose that the quadratic part of this first integral is also non-degenerate. We saw briefly here the classification of Dulac, but although we did not understand how Dulac arrived to this classification of quadratic centers for plane polynomial differential system of degree 2. So these are centers of quadratic systems. This is a copy-paste from the original paper of Dulac, which, as you see, it is in French. I'll just notice that there is a second, not a new theorem, just the same theorem, but seen from a more modern point of view in a paper by Cervon and Linz-Neto. And you see the equations are not quite the same. Here they are very explicit. On the other side, on the second version of the theorem, they are just some polynomials, P1, P2, etc. And we shall explain why this second form is more important for us. So I shall notice two things. First, how Dulac proved his theorem. At the same time, this proof of Dulac contains theorem, which I noted D for Dulac, and I said also that I learned this theorem from Cousin, and it is published in his old paper, and he gives credit to it to Linz-Neto. But at the same time, you can find a proof of this theorem in more recent books, like the book of Ilyushenko and Yakovenko, Analytic Theory of Differential Equations, a very recent book, a nice book that I recommend. So here is the proof of the Dulac theorem, the so-called Dulac method. What is the Dulac method? It is useful. Indeed, it is very classical. So maybe there are many sources. The purpose is to find whether a given system, analytic system, has a center. Because of the Poincaré-Lyapunov theorem, it will have a first integral. So we shall first look for a first integral which is analytic. How we do this? So you take some differential form and you suppose that it has a center. This differential form is not at omega. This omega. And as it has a center, and we suppose it's a Morse center, It means that the analytic functions, which is a first integral, we may put the quadratic part in a normal form, which is xy, for instance. It is important to be just this one, because this form will diagonalize one operator, which is just on the line after. So you take the form like this. So in fact, this is some elementary observation. If we have a center, the linear part can be put into this form. In terms of eigenvalues of the vector field, it means that the eigenvalues are plus minus I, the imaginary unity. And then some known omega 2, omega 3, etc. When by omega 2 I mean a homogeneous part of degree 2. dxy is the linear part of the equation. Omega 2 is the quadratic, omega 3 is the cubic, etc. You may suppose it is even analytic, but in the Euler case, we stop to omega 2, in fact, because his case is quadratic. Then, what we are looking for is this function f, which begins like this. Obviously, the function should begin by xy, because xy is already first integral of the linear part of differential equation. And we try to find first f3. f3 is homogeneous polynomial of degree 3. Once we have found this, we look for f4, homogeneous polynomial of degree 4, etc. If it is possible at each stage to find f3, f4, etc., we are done, we have a center. There are no question about convergence, but we now know that if the formal series exists, it is indeed convergent. Of course, it will not happen like this. Normally, we shall have some abstraction. Let us see what is the abstraction. Just let us examine the first line. Saying that we'll hear. Saying that f is a first integral, it means what? If you take the derivative with respect to the time, if we have a vector field, it gives 0. In terms of differential forms, it means just that the exterior product, omega df, is 0. So we develop this, taking into consideration the weight of the homogeneous part of omega and f, and we get a sequence of relations. Let us see just the first relation. It is what? On the left, it is something unknown, f3, we are looking for such f3. On the right, there is something which is known. The differential equation is given, omega 2. Moreover, we suppose that it's a family, because there are coefficients. So these coefficients will be parameters of our problem. And we want to solve this relation. It is easy to solve because, okay, if this correspondence on the left is surjection, so it can be solved for every omega 2. Is this a surjection? You compute. You take f3 general form of a homogeneous polynomial of degree 3. You take exterior power, you compute what is this. We notice that this gives us some operator which is diagonal already in the following sense. What is the differential of xy exterior product with differential of x power I, y power g? It is an easy computation, shows that when you derive xy, in fact, I wrote, well, there is a mistake there. And it's a differential of f3, of course. So you get what? You get I, dx power e minus 1, but here you cannot multiply by dx because it will give 0. You multiply by di, so we shall have dx di multiplied by x. And so you get again here x power I. There is some sign. And then for the derivation of y, it is the same. So minus I plus j, if I'm not mistaken, have to get this. So you can check whether I'm mistaken or not. So it is diagonalized in the sense that the monomial x, y, y, g goes to the form with the same monomial and some coefficient. So it's elementary. So you have a linear operator in this sense, which is diagonal, which is very nice. And if it is surjective, it is fine. It can always be solved. So in fact, there will be only a problem when minus I plus j is 0. Otherwise, you can always, so imagine that you have on the right side, instead of omega 2, some what is this in fact? Correct? Yeah, omega 2 is given. So let us know this relation. If I plus g is not even, for instance, equal to 3, this can never be 0. It can be only 0 when I is equal to j. When I is equal to j, we shall have some problem. There will be some obstruction to solve this equation for F3. So this equation for F3 can be solved, but if you go to F4, it cannot be solved for all monomials because of the presence of such E equal to G equal to 2. What happens? But what happens is that, for instance, dxy, exterior power of dy, is obviously 0, because, in fact, monomials like this xy power of something cannot be removed. So when you arrived at such a condition, it is a kind of abstraction. And you see, what is this abstract? Some coefficient. But what is this coefficient? Because of this form of product of exterior forms, this condition is some polynomial in the parameters. This is completely elementary. I don't write down the detail, but it's elementary. You find some polynomial, which is the abstraction. This polynomial in the parameters of the differential equation should be 0. And so what computed Dulac, it computed the first 4 in fact, with the linear one, 4 such obstructions in the form of some polynomials on the coefficients of the quadratic differential equation. And in each case, which he obtained, he succeeded to integrate the differential equation. And after integration, he finds a first integral. So he concludes that there is a center, in fact, and there is no need to continue to compute more relations. So this is the Dulac method. So what he proved, how to say, as something additional, is the following, that the center set of something is algebraic set because it is defined by algebraic relations, by polynomials. With the following detail, because omega is of the form dxy plus etc., it is equivalent to say that we have a vector field like this. And And he computed that for this vector field, for in his case of degree 2, there are just 4 relations, in fact 3, because the first is already satisfied, but some polynomial relations which give sufficient and necessary condition for to have a center. Okay, of course, if you have degree 3, you shall have probably more, and it will be much more. It will be much more difficult to integrate the differential equation. In this direction, the best results are due, namely, to Henrik Zuladek, which is present, which gave conjecturally complete list of cubic centers, but it is not proved. But it's quite possible that the list is complete. In any case, the list is much longer, and the computations are much more lengthy than in the quadratic case. And what happens if you have an equation of degree 10 or bigger? We shall have more. And is it true that it will stop? Of course, because of the Hilbert basis theorem. If you have some algebraic set, the ideal of this set is finitely generated. And because it is algebraic, it will be finitely generated. And by the way, in this way, we prove that the set of the differential equations which are polynomial of given degree inside all differential equations of the given degree with this normal form is an algebraic set. So what I mean by, once again, because this is important, we have a differential form. This differential form, we have some coefficients. Say, this is the cubic part, for instance, or maybe quadratic first, etc. We take the coefficients as coordinates. For us, a differential equation is just a vector, A1, B1, etc. In the parameter space, we have finitely dimensional parameter space. For instance, if we are in the quadratic case, we have 6 plus 6, 12 parameters. Of course, we can divide by some constant, in fact, to consider this not in C12, but in P, the projective space of dimension 11. But say in the quadratic case, we have 12 parameters. Inside, we have some subset, which is algebraic. So you have a vector space, a subspace, which is, in fact, algebraic set. This is the so-called center set. To finish the theorem, however, as it is stated here, theorem D, it's not sufficient. Why? Because we choose here a normal form. And the general problem will be when you take some arbitrary differential equation given by such one form, where P and Q are arbitrary polynomial of given degree, say D, degree D. So degree at most D. And inside, look at the subset in the parameter space of systems with a center. You can say, okay, but every such system can be reduced to this normal form if it has a center. That's true. So this means that every center of the more general system is in the orbit of the action of the affine group on this differential equation. What does it mean? Okay, what does it mean to put a differential system into some normal form in this case? It means exactly that we have done a linear change of the variable, eventually with a translation of something, and we do this. So it is not an analytic transformation, it's just transformation of this type. So this is the action of the affine group on C2. And modulo the action of this group, we get this normal form. So the question is, if you have some algebraic set, and we have the action of this affine group, it induces action on the parameter. How? But if you make some change of the variables, here we get some new differential equation with new parameters. So it induces an action on the parameter space. You look at the orbit. In this orbit, it is easy to verify that it is also algebraic. Why? Because it is explicit, more or less, although a little bit complicated, how this acts. You substitute and you see that every parameter, every vector in the parameter space is undergoes a linear transformation to another vector where the coefficients of these linear transformations are, for instance, in the quadratic case will be, or in the general case, will be some polynomials in the coefficients of the matrices A and C1. So everything is algebraic, so it is, how to say, one parameterizes the orbit in a polynomial way by some variables, some parameters, supplementary parameters. We shall get an algebraic set. So this proves this theorem. Okay. This theorem says that our center set is in fact algebraic set. Then I recall here briefly, so on 2 pages, the notion of irreducible algebraic set and irreducible component of algebraic set, which are not the same notions. So I suppose that we are aware, but let us say 2 words on this. What is a reducible set? So he is reducible, and he is irreducible. So this is reducible. So reducible is a set which can be reduced. In which sense? In the following, it can be represented like a union of other algebraic sets. Of course, this union should be non-trivial in some sense. If I take y twice, it's not the game. They should be neither y should be included in z, neither z included in y. And so this is the definition of reducible, irreducible. And we know that in fact these algebraic sets in the Zariski topology are in fact closed sets. So I recall that in algebraic geometry, one introduces a topology specific for the needs of the algebraic geometry, in which, by definition, algebraic set is just algebraic set. It is the same. So, in fact, this definition works for closed set in the Zariski topology. If you take another topology, not Zariski one, it will work also. It's very well to work with such a definition for arbitrary closed sets. The only problem is that when the topology is Hausdorff, you can separate 2 points with disjoint open sets. Then the only irreducible sets are the points. So it is not very interesting. So this notion is interesting only when the topology is non-Hausdorff, like the Zariski topology. And for this reason, this notion is not very much used outside this field, the geometry, the algebraic geometry. So, What is an irreducible component then? But imagine that you have a reducible algebraic set that you have reduced already like this in the picture. And imagine now that these y and z are irreducible. So we shall call them components. Of course, the question here is whether this decomposition exists, whether this composition is unique. And the answer is it's what you expect. We have unicity of this decomposition up to permutation, of course, can permute. And it always exists. So we arrived at the main question which motivates these lectures about the center focus problem. What is the center focus problem? But I propose to call center focus problem just this problem which is in red. Describe the irreducible components of the center set. And this formulation, to my knowledge, goes back to Alcides Linsneto and collaborators. So we can ask him. So this is, I would say, this is the modern version of the center focus problem. The classical version of Poincaré is, okay, we have a system, say if it has a focus or a center. So distinguish between a focus and a center. But from this point of view, it is, okay, there is some algebraic set. Describe the set. So the first step is to say which are the irreducible components of this set. And in this sense, the answer is given in the quadratic case almost explicitly here. The traduction of what is written here is the following. The space of quadratic polynomial system, the center set has 4 irreducible components. Which are these 4 irreducible components? In fact, they turn to be exactly what is described in point A. A, B, C, and the last one, G. And what about the others? It is not quite visible, but in fact, all the others are in the closure of the preceding. And thus they are closed, these components, so everything is fine. There are only 4. There are only 4. How it happens that they are in the closure? First, let us see what is the meaning of, say, A. A, it means that our omega is, in fact, exact. It is the differential of some polynomial. So it is called Hamiltonian system in this case. It has a first integral, which is polynomial. The second says that our differential form is of logarithmic type, which was the topic of the preceding lecture. What we saw in the preceding lecture, these were the differential systems with the first integral of this form. And if you take the differential of the logarithm of this form, you shall get exactly what is written in the theorem. Of course, in order to get a quadratic system, you cannot take polynomial of a big degree here, because the degree of this form, of course, you have to multiply by f1, f2, f3 to obtain a polynomial one form. And the degree will be 2 if the degrees of these functions is 1. So if the degree of these functions is 1, that's, say, linear factors, product of lines, then the notation for this stratum, this irreducible component of the center set is this one, and it is classically called Lotka-Volterra. Volterra component. Well, the second component, point C, it is very similar, but you have two factors only. So you have just f1, a first integral of this form. And in order to get a quadratic system, we have to suppose the degrees are 1 and 2, and you get so-called reversible component. Reversible irreducible component. Why it's called reversible? Because if you take the level set of this first integral, you get what? One quadric and one straight line. And by affine change of coordinates, you can suppose that your quadric is just a circle, and your line, it's just like this. So it is not restrictive. But in this case, you have asymmetry, involution, which leaves this configuration, this polynomial, not the polynomial, this function invariant, so the corresponding foliation is invariant. So there is a symmetry. So these are A, B, C, and the last one is the so-called codimension 4 component, which is characterized by this, that the first integral is a ratio of a polynomial of degree 2 and a polynomial of degree 3, but which are special ones, because if I take arbitrary polynomials, the degree will be 4 and not 2. So they cannot be arbitrary. So to check what I say is maybe, so here is the list of these 4 irreducible components in the quadratic case with the classical denominations: Hamiltonian, reversible, Lotka-Volterra, codimension 4. Here is an example how you check, for instance, that the case D is not a new case. So what was case D in the theorem of, in this form of the theorem? D, so Dulac discovered that if you can write down in this form D, you see some Py, Pg, dpy over P1 plus dp2 over P2 with some coefficients, lambda 1, lambda 2, plus differential of Q equal to 0, we shall have a center. But in fact, this is in the limit. This can be realized as a limit of points in the standard irreducible component, which is the Lotka-Volterra case. So here is the check. I even cannot call it a proof, just a check. Take such a differential logarithmic form when you have P1 sur P1, P2 over P2, and then you take 1 plus epsilon Q divided by. So certainly all these are polynomials. Epsilon is a small parameter. And when you take the limit epsilon tend to 0, you get just a system of this type. The first integral will contain exponential, as was noted as an open question at the end of the talk of Paval. It is interesting to look at exponential. But the exponential, as we know, appear as limits of polynomials. So the exponential are just polynomials, but hidden after the limit. So this is an example how exponential appear. From the point of view of our point of view, which says, okay, we have to look at irreducible components, it means that this this one is some special point on the border of some component. We have some component, which is this Lotka-Volterra component, and here you have some special point inside. But it is not a new irreducible component. So it is not indeed a point which deserves so much attention, although it's a special point. Okay, so here there is another similar case, etc. And so all the cases are verified like this. And so if you compare all these considerations to the initial theorem of Dulac, you see that the theorem of Dulac, one does not understand anything. There is just some list of systems which by chance turn out to be with a center. And now it is completely different. In fact, there is an important result of Zoládek, who summarized the work of several generations, in fact, mathematicians on this center problem for the quadratic systems, which says that, okay, here is an explicit description of the 4 irreducible components written in a very economical way. So as you remember, at the very beginning, I said briefly that there is such a trick how to pass from real two-dimensional system to one complex variable, that is to say, identifying R2 to C in the case, of course, when x, y are real. Sorry, here is one. So the meaning of this z is just x plus I. Why? If you have a focus, I said that the focus takes exactly this form, I plus alpha or lambda is written there. This is the normal form of linear focus in which we have performed a real linear change of variables, so not a complex one, but a real change of variable. It's important because here you take xy real, so you don't have the right to make changes with complex coefficients. Then there are, of course, in our case also quadratic. But everything which is quadratic is what? Either z square or z bar or z bar square with some coefficients. Moreover, this coefficient can be here complex because we already used a complex number here. So it means what? In fact, it contains on a single line 2 equations. Just you develop this, you take the real part and the imaginary part, and you reconstruct the initial real polynomial differential system. And using these notations, we have this description of the 4 irreducible components. But attention, it is simple because we took this normal form. That is to say, the center is at the origin, and we have a standard focus. But in general, in full generality, we want to describe this center set for arbitrary polynomials p and q, say quadratic, without saying that the center is at the origin. You may say okay, it's almost trivial. You just make a translation, then a slight rotation. Okay, this is called action of the affine group. And the fact is that a similar description in the general case is not known in the literature, which is curious. And we shall see why now. I suppose that I know more or less the answer why, and I shall argue now why this center set is not given in the literature in full generality. It is because probably it is impossible to give it like this, but let us see what happens. Here, what you see, Jolanden will recognize a page of his paper, the same paper from which I took the theorem, the preceding theorem. Here we have a picture of these 4 sets. So I shall explain a little bit what is pictured on this picture. So these 4 sets are considered as, we have center set which has 4 irreducible components. We take only the real part. So in this case, we have a real algebraic geometry in some sense, because to make a picture, it is easier to take a real part. Moreover, in this way of writing, we have supposed that all coefficients of the equations are real. Here they are complex, but when you pass to variable x and y, it is allowed to have only real coefficients in order to have this to have a sense. Okay, how many parameters we have in general? In general, we have 12 parameters, I said, or 11 if I make a reduction multiplying by a constant. Inside, it happens that these first 3 strata are of codimension 3. The meaning of this index 3 is the codimension, while Q4 means codimension 4. If all the parameters are 11, if you remove 3, we have 8. So it's an 8 parameter algebraic set, even probably with singularity, even sure how to describe such a set. Okay, but we have the action of the affine group, which is what? Affine group is just one matrix, which is 2 by 2. So it makes 4 parameters, plus translation, which makes another 2 parameters, makes 6 parameters. We can reduce taking a quotient. Suppose that it is possible. And it is indeed possible, but it's another discussion. So you remove 6 and you obtain 2. 8 from 6 means 2. So in a sense, modular dimension, so dimension after taking quotient is 2. So here we see 3 sets of dimension 2. So these are dimension 2. These are the first 3 one. Lotka-Volterra, reversible Hamiltonian, plus 1 of dimension 1. So this is the last set of codimension 1, which is the so-called, this one, special case of codimension 4. After reduction, it will have dimension 1. And so it is the picture, according to Henrik, of the situation, which is, for a long time, I think even now, it has some importance. It shows the different intersection, although it is there is somewhat misleading in this picture. So first, we have the impression from the picture that the Lotka-Volterra is union of 3 irreducible components, which is not the case. Second, this real picture. So what to do? The complex one is more complicated, maybe. Finally, this picture concerns only the normal form in which the center is placed at the origin, and the linear part is a standard focus written in such a way. And in full generality, what we know now is that we have 4 irreducible components. We may wonder, these irreducible components, is it true that they look like this real picture? For instance, what kind of singularity can have these irreducible components? And so we shall see now that they can have very special, very interesting singularities. And we enter in some domain which is not explored until now. What is not explored is the structure of these irreducible components, even in the quadratic case, because I recall that we are in the quadratic case, something extremely classical, very well studied, etc. Still, it is not well known what is the structure of the irreducible components in full generality, that is to say, for the general quadratic system like this. So let us examine, for instance, the singularities of the first case, A, in the list of Servo-Linz network, which is a product of 3 lines, this one, this case. So we have some stratum, so some variety, which is maybe not, has a singularity, is not necessarily smooth, which is invariant under the action of the affine group, the induced action of the affine group, and which is parametrized. So it means it is some special variety, relatively simple. So it is parametrized by how it is parametrized. So it is a product of 3 lines, so it is parametrized by these lines. I noted them L1, L2, L3. Here they are F1, F2, F3, so these are the same. By line I mean here just a linear polynomial of degree 3. It has 3 coefficients, so these 3 coefficients are taken as parameters. And also we have powers, alpha 1, alpha 2, alpha 3. So you have some set of parameters which very well parameterize, so an affine space parameterizes our variety. This already proves that it's irreducible, by the way, according to some not very complicated theorem, which says that the image of an irreducible is irreducible under morphism. And here this morphism is even quite explicit, linear. And okay, it's not linear because we have multiplications, but it is given by linear functions. So we have this parameterization, and we can, to check whether a given point is smooth or not, we can compute the differential, and we can study this question. It's accessible. But there is another possibility also to have a self-intersection. So for this map, that is to say, locally you may have embedding. This blue piece is a diffeomorphic image of something, and this, say, yellow piece is a diffeomorphic image, but globally it's an immersion of some variety, for instance, of C10, some affine variety. So let us check where this is possible. What this would mean that we have such a self-intersection. It means the following, that one and the same differential equation is represented by 2 different first integral with different parameters. So you see I gave there some parameters, alpha 1, alpha 2, alpha 3, and 3 lines. But imagine that there is another combination of 3 lines and 3 parameters. But it gives, after computation, exactly the same differential equation. We shall have this. In fact, it is what happens. So let us suppose that a differential equation has 2 first integrals. One like this and another similar, but with different functions, so they are missing tilde. So we have L1, L2, L3, and maybe there are another lines with powers, which are maybe not the same. Why not? From this we may deduce, if this happens, and it may happen, we deduce that, in fact, we have a rational first integral, which is completely transversal to what was done in the previous lecture of Pavao. where he supposed that these are essentially irrational numbers. But here, in fact, if these are first integrals, this implies that the following rational integral holds true. As Hossein explained to me, this is an idea of Joannoulou. That if you have such first integrals, it is elementary indeed to check that there is a. Everybody can verify that under the hypothesis that this first function is the first integral, this second, then this rational function is also first integral. The proof is on the next page. Okay. And so we get such a first integral. But if you look at this first integral, you may say, okay, but now we have 6 invariant lines. It's too much. Is it possible? For instance, a quadratic differential equation can have only 4 singular points. And if you try to trace 6 lines, there are very limited positions when all the lines should be parallel. But in fact, you can check in this way that a quadratic system cannot have 6 invariant lines. In fact, it can have only 3 non-parallel lines. In fact, exactly 3, because this is topological fact if you count multiplicity. So it can have 5 at most invariant lines. Among them, at most 3 are non-parallel. Non-parallel, it means they intersect still, but at infinity. You cannot have 3 parallel lines, things like this. All these are elementary facts that you can verify very easy. As you cannot have 6 lines, it means that one of them should cancel. Right? There is the only possibility. If these 3 linear functions are distinct, mean non-collinear, so we have a contradiction. So something should cancel. And so our first integral is of this form. But in this case, it is also easy to check that the homogeneous part, which is of degree 2, of the numerator and denominator are collinear. So essentially it means that if I take minus some constant, we get some line, some polynomial of degree 1. Maybe L1, 2, 3 are not the same. Take prime. Have something like this. So all this can be done rigorously. And the conclusion is that it is possible, if this happens, to have only if the first integral is of this form. Excuse me, the chairman, at which o'clock I have to finish to control? 5 minutes? 2 minutes. 2 minutes, so. Okay. so I go directly to the polynomial. So by linear change of variables, affine, we can suppose that these lines are in some canonical form. So for instance, take this one, because historically it appeared in several papers. What is this? This is a polynomial which has the following property. If you take f minus 1, I get x squared plus 1 minus 1 squared. 1, 2. So, miracle, we have the same differential system. For sure it is the same because this is the same first integral after differentiation. But the parameters, the coefficients are not the same. We shall have just this. in the parameter space. If you picture the phase portrait, it is easy to picture. We have one line, y equal to 1/2. Note that this is a product of two lines. X squared plus x squared is a product. So you have a center here and center here. We have a double center. The system is still Lotka-Volterra, which, as we know, have only one more center. But this is a special system, which is on the border, how to say. And so this is this. And I shall finish with this picture, which explains the situation. And in fact, we have a monodromy. What is explained on this picture? So first we recognize it in the middle this phase portrait. This is the phase portrait of this polynomial. What is claimed is that in the parameter space there is some loop like this. So on the center set L111, that is to say Lotka-Volterra irreducible component, we have some loop like this. And for each point on the loop, we have pictured the phase portrait of the corresponding system in a real domain. So what happens? When you go, you see, when you move a little bit slightly far from this double center, we destroy one of the two centers, say the second or the first. And when you go along this loop, and when you come back, we exchange the focus and the center. So there is a monodromy, which cannot be removed, of course. And when you go to this self-intersection point, we have a double center of Lotka-Volterra component. So this is the nice picture, which, by the way, just as a curiosity, the same differential system I found last week in a paper of Linz-Neto in another occasion, exactly the same differential equations, but more curiously, I found the same differential equations, that is to say, this one. It can be written like this after change of variables. It's another normal form of the corresponding differential system with such a first integral. In the famous paper by Petrovsky-Landis, where he proved the Hilbert-16 problem, proved with a wrong proof for the quadratic case. Exactly in this paper, it is the system which he uses to perturb and to show that in a complex domain you can have at most 3 limit cycles. This one. So it's curious. And I shall finish with that. The next 3 pages are references. And some conclusions. One of the curious conclusions of all this stuff is the following, which is like a scandal. The Bautin ideal not always is polynomially generated. What I mean by this? It's a little bit speculation. The Bautin ideal defined by Bautin, of course, is polynomially generated. What is Bautin ideal? If you take in a more general context such a differential equations and say, okay, there is some focus and sometime it can be a center, we can compute the first return map, and like Bautin did, you can compute the coefficient of this return map, and it defines some ideal, which we shall call Bautin ideal. The theorem is then that it is not polynomially generated because of this picture preceding one. Why it is not polynomially generated? But suppose that it is, then when you move, then suppose that it is the ideal of this branch, the lower one. So this corresponds to this center, but not to the other. You see that we can move along this branch and we destroy the second center. It is the ideal of this center. If it was polynomial, because of the irreducibility of this component, it will be 0 automatically on the component. So the second center will persist. It cannot be destroyed. So this is a contradiction. It shows that the generators of such an ideal can be only analytic. So conclusion, Boolean ideal is not polynomially generated. But of course, I mean the Boolean of this. This maybe explains why we don't find in the literature this ideal explicitly, because if it is not polynomial, how to describe them? You can describe the variety eventually, but if you go in this direction, just the ideal corresponding to the center of a given center, we shall not arrive because it is analytic. So I shall stop here. And I finish with some references which are directly concerned with this talk that we can check later. Okay, thank you for the attention.
Okay, questions?
It's too late for questions.
So in this example, when you have a self-intersection in the logarithmic component, there are at least two residues that are equal. Yes?
At least two residues?
That are equal. Am I right?
Yeah.
Two ones.
Yeah. You have one minus one. You have power. The powers here. One.
Is that true in general? That if you have two residues that are equal, you have a self-intersection in the logarithmic
from the point of view of the parameter space, the picture is a little bit like this. We have here the stratum of this Lotka-Volterra, say L11 and 1. Something two-dimensional. We have, say here, the stratum of, say, reversible, 1, 2. I didn't show what happens on this stratum, but systems of this type exist here also, and they form something of codimension 1. And this curve then intersects the other on the intersection of two strata, and this is this one. This is a single isolated point on the Lotka-Volterra, which at the same time belongs to the 1, 2, because you see here polynomial of degree 2, polynomial of degree 1. But this is reducible, so it is on the intersection already between L12 and L11. But I said that L11 has a self-crossing here, so it is difficult to picture, but this variety self-intersects here at this point. But at the same time, the other variety self-intersects along the red line. Okay. So this is, how to say, the global picture, which I...
Because it could be a self-intersection without being an intersection of two components, right? But in that case, it happens that...
In principle, yes, but what I found is this.
Okay.
So this is the... I didn't look at the last components, the dimension 4. Also, I don't know whether there are other singularities, but the self-intersections are like this. And then continues. Okay. What I want to say is that in general, the question is not studied, and it's an open field, and what will be the singularities in cubic system for cubic, etc. Maybe, probably it is true that there are some special rules. We know some of the irreducible components. Hossein have proved many years ago that the logarithmic components are irreducible components of the center set in any degree. So for such a component, for instance, what kind of singularity you can have? Clearly will be self-intersections, it is easy, but let us classify. This is not done. And so there are interesting questions. Even in the most classical question, like the center focus problem, which has exactly the same status as the 16-Hilbert problem, they are not solved. So it's very challenging for young people. Solve them 1 century later. So, yeah.
So, young people. Any other question? About?
You are free to make any excursion in beautiful
But not in the night, maybe.
You can put a t-shirt of Copacabana. And then be careful about the robbers.
Okay, let's thank Lubomir again.